that reinforcement learning. Today we are going for this thing. So now we are starting that. First, we will go ahead with that introduction of hierarchical approach. That what are the different mechanisms that we will go through that in hierarchical approaches. So basically, what happened? The hierarchical, what happened? Hierarchical, you know, no? What will be the hierarchical meaning? Will be there. Hierarchical means that you are having a root will be there, then their child will be there, then sub child will be there. Just like that tree structure you have been seen, no? Where one hierarchy will be there, and according to hierarchy, different levels will be there. So basically, this hierarchical decomposition, what we are doing there, we are having that the complex, we are carrying that complex problems are there. So we divide these complex problem into the smaller sets, and then we interrelate these problems with each other. If we are compiling that complex problem in a one, so it will be a very problematic for computational. So that's why we will decompose into that small, or in other words, what we will say, that in smaller problems are solved that separately, and the result will be combined and to find the original problem solution. So that is clear. So it is known as Navy application of reinforcement learning. What it will known as, it will known as a Navy application of reinforcement learning technique that fails to scale more complex domains will be there. You have seen that while we are just going for that this one software development. In software development, what happened? The software development is having that the entire software is divided into different teams, and different teams are working on it, and that's one same thing we are using in the reinforcement learning for the same. So what happened here? They have introduced that hierarchical approach will be there, and what will be the main motive will be there? What will be that reducing a reinforcement learning problem in a manageable size? That is the main motive for this. Next, this hierarchical reinforcement learning, the observation that we are using, that is the HRL is there. So what will be there? It was basically what happened. Some of the actions and the states and their abstractions we are using in it. So basically what happened, it is a method of reinforcement learning that can be extended to work with abstract state. First one is your abstract state, and what are actions over a hierarchy of subtasks will be there, and decompose the original problem potentially using the complex computational complexity. What will be that that it was going to tell you that whatever that you are having, that is original problem will be there. So the original problem is bifurcated into, that was decomposed into different small problems will be there. That is sub problems will be there. And in that sub problems, what we are doing, we are having some abstract states will be there. On these abstract state, we are putting down some actions of that hierarchy. And how we are getting, this is our original problem is this one. So when we get that solutions of this one, this one, this one, this one. So when we combine that all these solutions, so what we are getting that original problem solution you are getting from this one. So what will be that the benefit we are getting from there? So whatever the computational complexity, if we will be computing this original problem with on a moment, means only that once a moment, so their computational complexity will be arise. So to reduce this this computational complexity, what we have been done, we have been bifurcated into sub problems, and every sub problem they are having any abstract state will be there, and according to that state we are performing some specific actions will be there. Okay, now we are considering this with the help of that an example. We are treating that example will be there. So the various concepts and approaches we are using in it. We are using various concepts and approaches, and we are having the algorithms are there, which are basically designed for hierarchical structures, and they are working towards for hierarchical reinforcement learning. So now we are just artificial intelligence is about to how to construct agents that act rationally. That is clear now. In that reinforcement learning, whatever we are doing, that will be done with the help of that an agent. Clear. So an agent acts rationally while when it maximizes a performance measure given a sequence of perceptions will be there. That is clear. We already studied that thing. Then what will be the next one? We are planning it. We are control the theory, and what will be that we have been we are viewed that perspective and including that what kind of problem class that we are going to deal with. So in reinforcement learning, first it seems like that we are having the iterative approach to solve an artificial general intelligence problem. So basically in that we are just considering about that agent and how the agents are working, how the performance will be there, and what are their performance class that will be going on there. So now this is the most important. While in principle this may be true, reinforcement learning is beleaguered. The beleaguered means we are having that different situations where we want to work out. Clear? The curse of dimensionality. What is that meaning of the curse of dimensionality? Meaning will be there. First, that will be introduced by the Bellmans will be there. It indicates the number of samples, whatever the number of samples that is needed to estimate an arbitrary function with a given level of accuracy grows exponentially with respect to the number of input variables. That is the dimensionality of the function. So that is clear that what is that your curse of dimensionality will be there. It was stated by the Bellman's scientist. After that, what happened? The curse of dimensionality is the term that will be same thing. What is the state space and the additional variable that we are using in concern of that our problem. So that will be going on there, and we are having we are dealing with the complex problems here with the help of this curves of dimensionality. We will check out in that different dimensionalities according to that these different means state space and these things we are achieving towards our goal. So now, fortunately, in that real world, it is highly structured with many constant and with the most of the parts independent for that other parts will be there. So without structure, it would be impossible to solve a complex problem size. If we are not having the structure problem, if we are not having the structure thing, so how you can solve that thing? So structure is the most important thing while we are solving in that hierarchical this way. That is the significance of structure it was telling to you. Then structure can significantly reduce the Navier space generated by shear elimination. What that means, we will discuss with the help of that how that this thing will be achieved. Right now, only remember that Navier space generation will be there. For example, if transaction and reward function for two variables are independent, if we are having the two variables will be there, one is the transaction and one will be the reward will be there. They are two independent variables. Then reinforcement learner would only need to explore state space size. What will be the state space size will be there. That will be for the addition of state space size of the variable instead of one the size of their product. So what basically they are doing, they are going ahead for this one state space according to this means example. So in that reinforcement learning is concerned with problems represented by that different actions will be there. We are having that different actions will be there. According to that, we are having, we will perform these actions on that well states will be there. We are generalizing the problem to solve them in a dynamics in a time. Hence, we often do reinforcement learning problems as tasks, sub problems, and this will be there. So same thing, whatever that the main problem will be there, it will be decomposing into small problems. So here we are dealing with that problem as a task, and whatever sub problems they are treated as a sub task will be going on there. Now, empirically, what will be going on there? A large portion of complex systems seen in nature, and what we are doing, we are accept that hierarchical structure for the same. By hierarchy, what that means? That means the system is composed of interrelated subsystems that in turn have their own subsystems. So what that means there, what will be that hierarchy will be there. In that hierarchy we are having composed of interrelated subsystem. Why that term interrelated subsystem should become, I am giving one example, and that turn have their own subsystems and so on. If we want to do that, our main function is that we want to get average will be there. Okay, to calculate the average, what we are having, we have created that this with that some average of that best 5 students in that class, or we count that topper of 5 student in class. So what we are doing here, we will decompose now. What will be our target is to get that top 5 student in that class will be there. What we are doing, we are here, the problem is that whatever these top 5 students, how we are getting, We are getting now first what we will do. We have been decomposed according to the subject wise. According to subject wise, individual students, they're having that their marks will be going on. So one total will be came. Whatever the total marks will be came, then these individual totals, student 1, student 2, student 3, and so on, whatever the students will be there, up to that these individual marks will become. After that, in that individual marks, what we are doing, then we will bifurcate it into that different categories, either that comes in first category or first division, second division, third division will become. After that, what we will be do, whatever, because we have not required the third division and second division, so we will go through the first division. And in first division, what we will take that first best 5 students. So our problem will be that solved. So this is the hierarchical way where that we are having some major problem will be there. In that major problem will be that bifurcated into sub problem, and these sub problems is having that they are having that subsystems will be there, and subtasks will be going on there. So same we have been using in that human societies will be there. We are having the hierarchical organization will be there. To complex tasks dating back least that will be not using by right now. It will be using with the ESTM times. Long back echo that these things will be using. So basically what happened, what will be the property that we are using, that the main concept will be the decomposability of that will be that sub bifurcation of that main problem into the sub parts, and whatever the decomposability will be there, we will simplify on the basis of decomposability what will be the behavior and what will be the description for the same. Now we are having that heuristic form Polya 1945 for this will be a mechanism for there for problem solving, decomposing and recombining or divide and conquer in today's parlance if we are using. So many large problems have hierarchical structure that allow them to be broken into the sub problems that we are using. And these the sub problems being smaller are often solved that is more easily, and less computational power will be required there. And that what will be the time that will time taken for these small problems to solving, that will be very less if we are comparing. The solutions of these some problems are recombined and to provide the solution of the original larger problem that we have been discussed. So the decomposition can make finding that the final solution significantly and efficiently with the improvements in time as well as the space complexity for both learning and execution. While you are designing any algorithm, so what we are checking, if we are checking that particular algorithm will be working with, we are having 2 parameters will be there. Na? One is time and another will be the space will be there. So same thing we are using there, time as well as the space for the same. In many ways, this hierarchical reinforcement learning is about structuring reinforcement learning problems, much like whatever we are having the computer programs will be there, just like we are having that subroutines will be there, and we are having subtasks will be there, higher level reinforcement learning problems will be going on. So just as the main program called subroutines, and higher level reinforcement invokes that these all subtasks into one place. We are having that using this sub problem subtask concept in OOPS also. We are having that one class will be there, and in that class we are having subclasses will be there. For basically what happened, all these things will be belonging to one class. Now here what happened, now we are going through that one on that example will be there. In that example we are having 4 room tasks will be there. In 4 room tasks you will be somewhere that we are having that these 4 quadrants will be there, and this will be the exit sign will be there, and this will be your current position will be there. So this current position will be there. So what will be there, how that agent will be there. So agent will be interacting with an environment. Agent will be act, and according to that particular environment he will be sensing, and according to what step he have been taken, what action will be taken, that action will be coming to either in reward category or the punishment category. Now what will be going on there, what will be that we are having that what will be that
basic inputs will be there, what will be our assumptions will be there, what will be our target will be there, that we are discussing that about that 4-room task now. That is clear now. Now that we are using in detail that how we are using. So in this this 4-room example, what happened? Agent represents as a black oval. You have seen that thing, no? This agent is using as a black oval. This is the black oval will be there. The location will be southeast room of a 4-room house. So where is that location will be there? That is the location south. This is the location will be southeast. So this location will be right now that particular this agent will be that will be represented by the owl that was in southeast state. Now the room are connected by open doors. The northwest room has a doorway leading out the house. So what happened? We are having the different doors will be there. This is also a door. 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 But we are considering this one here. We are discussing this one. That will be the northwest room has a doorway leading out of this house. So each time what happens when the agent is taking any action and receives a sensor observation and a reward from the environment will be came. So what will be going on? What will be the target of this particular agent will be there? He want to exit from these 4 rooms. This is the first room. We are just comparing. This is the second room. This is the third room, and this will be the 4th room will be there. Okay. So these 4th room, every room is having that doors will be there. But what will be that source will be this one, and what will be the target? Target is this one. He wants to get out, means to get outside from this room. So how what happened? Each cell represents a possible agent position. What will be there if the agent will be there? So it was representing a cell. This area will be representing as a cell where this oval will be right now there. Now what happened? Each cell represent a possible agent position will be there. The position is uniquely described by each room and the portion of each room. What that means if we are using and this grid, this problem. So what happened? We are having that x-axis and y-axis will be there where that this interacting will be there. So in that particular room, whatever the positions will be there that have been predefined, that already we are having the values of this position where these positions will be relying. In this example, we are having that similar, all these, what will be that problem will be there. We are having the similar dimensions will be there and similar positions will be there. What that states, that states, whatever the dimensions will be there. What dimensions mean? What will be the size of this block will be there? That all the blocks is having that equal size will be there. Okay. And same identifier. So what they are having, the value of this will be also same, this will be also same, this is also same. So all that identifier value will be same. But what will be our target? Our target is whatever this oval will be there, this agent will be there. He want to get outside from these all 4 rooms. Clear? Now, the environment is fully observable by the agent, which is able to sense both room it occupies and its positions in the room that will be there. So the agent can be moved. That the here what will be the meaning of the move? Whatever the move it was going on, what that means? One cell step in any of the 4 compass directions at each time. What that means? That means if our agent will be there. Wait for a moment. I will just rub it. Now, what happen? What will be the possible movements will be there? The agent can move 1 step. What will be that step will be there? 1 step means either this agent will be there. It can move this side, right, left, top, or down. These are the possible ways the agent can be moved. We are assuming that thing. So that is the state now. Right now, if this agent will be there, what how many directions it can move? It can move 1 step ahead this side, 1 step ahead this side, 1 step ahead this side, and 1 step ahead this side. That is clear. Now, what will be going on there? Yeah. it also receive a reward of that whenever it was going to that any step, maybe that we are having that what will be that if it was interacting with that boundary of that particular that room will be there, so it was getting some that dark values, or this will be there, minus will be there. So what they have been assumed, that it also receive a reward of -1 at each timestamp, whatever timestamp will be there. What will be the main objective will be there? The main objective of this is least cost route find out, whatever these four rooms have been given. Na? These are the four rooms will be there. Every room is having some that is way out of to get from this room is there. What is our target? We will be there, and whatever the movements we will be do, that will be the optimal, and we will achieve our target. This will be there. So we are assuming these actions will be stochastic here. What we are actions we are using, they are in stochastic nature will be there. So when any action will be taken, there is 80% chance that the agent will be moved in the intended direction, and 20% is chance it will stay in the place where that will, if then will be there, means that was in negative. We are talking about that the reward will be here, the punishment. Punishment means it was going in negative direction. It was not going for this one. If the agent moves wall, it will be remain where it is. If the agent, if just like that, if our agent will be there, right now this agent will be there, we are assuming that the agent have taken this step. If any step that agent will be taken and where that wall will be interacting, here the wall will be interacting, what happened? The agent will be in their remaining space. Now it will be going there. If the wall will be interacting, so what happened? It will be there. So same state will be there. But if he uses this one to that for moving in that direction, what happened? It will be having that this position, whatever the action he have been taken to move this side, then the state of the agent will be changed. Okay, so that is that basically this is used for the four-room task. Now we are discussing this HRL, what is that hierarchical reinforcement learning with that MDP, Markov decision process. We have already discussed in our previous discussions about MDP. So we are taking that the reader can easily verify that four-room task in such reinforcement learning problems. We provide here initial innovative description how that hierarchical reinforcement learning methods might be applied to four-task room. Now we are taking that how we are deploying these things in it. If we want to find a policy to leave a room, say by the north doorway, then we could use this policy in any of the rooms because they are identical. So what that means, if we have made that one policy for that one room, in that one room, this way, how to that get out from that particular room. So same policy can be used for the other rooms. Clear? So the problem to leave by a room by the north doorway is just another, albeit smaller reinforcement learning problem that has generated the position in room states, actions. What will be the actions will be, states will be there, actions will be there, transactions will be there, and what kind of reward functions we are using with that original problem. So we proceed to solve two smaller reinforcement learning problems. One is to find a room level, room leaving policy, what room policy we will find out. And next one will be the to the north, and another leave a room through the west door. Clear? That will be there. So we will first will make a that policy for the same, ki how to that get out from a room, and that is concerned with that whatever the doorway that is associated with that particular specific room. Why this concept will become for why they are telling that is a specific, because here what happened, whatever the policy we are making for this one right now, it will be there. So what we are assuming, either we are assuming for this direction or this direction, whatever the policy will have been made. We have made, for example, we have taken that policy, whatever the policy we have been made, that we have been considered this door. So while whatever the policy, whatever the computational and whatever the actions to require to get out from that particular room, we will not use the same policy for the same. We will, whatever the actions will be going on, whatever the computational and these things will be going on, the same policy can be used in that another room But the door, what will be that the policy consideration will be there on which side that particular doors will be there and what will be the way of exit of the specific room. So this policy will be depending on these two factors. Clear? So that is clear. Clear. What I am telling, that will be there. At this stage, we simply reward of -1 per room living actions. We have having some values will be there according to these values we are using. So here, what happened to temporarily using this along with this hierarchical reinforcement learning with MDP. Here we are using semi-Markov decision process. What we are using, that is the most important thing in hierarchical. What we are using, we are using SMDP. What SMDP stands for? SMDP stands for semi-Markov decision process. Once learned the execution of higher level housing level policy, if we are having that housing living policy will be there, that will be determined for the room living actions will be going on. That same thing, whatever I have been discussed with you, same things will be in that these 2 points. Okay. And this policy, whatever the policy we have been going to, that whatever the actions will be there, that actions will be working up to that what will be target, the final will be leaves that particular house when he will be exit from that particular house. So now we are having that some approaches for hierarchical reinforcement will be there. So now we are considering with the historical perspectives. In historical perspective, Ashby is an scientist will be there in 1956. It is talking about amplify the regulations of large system into the series of stage and describing these hierarchical control system. And these hierarchical system will be known as here, that is ultra stable. What nomination they have using, their nomination will be using ultra stable. So whatever this HRL, that is hierarchical reinforcement learning will be there, it will be used at the gating mechanism will be there. We are having a gating mechanism will be there at what level, that will be at higher level. It will be run to switch in appropriate and more reactive behavior at the lower levels that we have been doing. So in that was in 1956. In 1952 also they have been proposed a gating mechanism for an agent that will be recurrent situations. Recurrent means where the same situation will be came again and again. So the what is that subsumption architecture works that will be for that. What that means, subsumption means whatever that the other we are having that other similar problems will be there. So we will use that the same architecture for the same. So it decomposes what it was doing. It was decomposing the complicated behavior into the simple tasks, which are originated into that different layers will be there. With higher level of layers, it became that increasing. If we are having increasingly that what will be the increase there, the abstract will be increasing. And each layer we are having that whatever the each layer's goal will be there, we are having the subsumes will be there of its child layer. For example, obstacle avoidance is subsumed by a forging for food parents task and switch in when an obstacle is sensed by so that is an example they have been taken. You can take any example for the thing. Now we are having that we using this historical perspective in that that is MDP. Now in that example what we are taking, we are having that top level will be there. In that top level, like the navigator of the 18th century, they have been taken that if we are in 18th century, whatever our ships will be there, so their ships are floating, they are just doing their journey in that sea. So what happened while doing their journey, so they want to that which direction they are going, how much time will be there, how much that fuel will be going on. So in 1992, basically they are having that they are also using that kind of gating mechanism will be there, where that this Hellman's that is that particular this Hellman's in 1992 they are describing and they are giving directions to sail. And here whatever the this gating mechanism they have been developed, this gating mechanism they will be used as hierarchical DYNA. that is hierarchical DYNA. Okay, that they have been used. So in that DYNA, whatever this DYNA that we are using in reinforcement learning, it was using both things. What will be the real situation will be there, and what will be the simulated experience that after building a model, what was the model we have been simulated, and what will be the reward and the state transaction and their functions we will compare with them. So what happened here, this HDYNA model, first what will be going on, what it learns elementary tasks, such as to navigate to specific goal location. Each task is treated as an abstract action at a higher level of control will be there. So this will be, this all will be concerned as what we have been discussed, that is HDYNA. We have been discussed. Now it is the idea of that decision model should be constructed as crossover that granularities further up the control hierarchy. So what that means? That means we are having that discrete composition and finite grain material or system will be there, where that means whatever the large subcomponents will be there, we will find these grain according to the description, and whatever the smaller components will be there, that will be composed from that larger ones that will be going on. So this hierarchical, we are using that hierarchical distance to goal will be there. One algorithm will be there that will be Kalbing in 1993. That this algorithm will be introduced by Kalbing 1993. In that, what happened? The idea of decomposing that according to that the value function from the distance component along with the path goal was discussed in that specific algorithm. So HDG is modeled or navigated by that particular landmarks, and it was working on these principles. So we are having that different approaches for the hierarchical reinforcement learning will be there. What are the different approaches will be there? We are having what options we are carrying out: a formulation of abstract actions, HAMQ, partial problem approach, and MAXQ, value function decomposition, including that date. These two, what is that HAMQ and MAXQ, that we will discuss in our tomorrow's lecture. That is there, no?